Good morning, everyone. So we're going to continue in Chapter 7 here today, get to some review questions also from Chapter 7. So pretty quick chapter for us, and we might even get a little bit of a start into Chapter 8. So Chapter 7, just as a reminder from last time, we're only covering sections 7.1 through 7.4. So we're only covering about half of the chapter. So continuing on our discussion with ionization energy, I think we were on this slide when we were ending class last time. So the first ionization energy is the energy that's required to remove the first electron from an atom. So if we were to look at sodium, for example, it was 496 kJs per mole. So that would mean that the reaction of sodium as a gas, forming sodium still as a gas, but with a positive charge, having lost its one valence electron, that this reaction here would have a delta H or an energy change associated with it that comes from that 496 kJs per mole. So the energy change of that reaction is what corresponds to that first ionization energy. And then the IE2 would be the energy associated with kicking a second electron off. So the IE2 for sodium would be sodium gas with a positive charge going to sodium 2 plus, which you would probably imagine isn't too likely to take place. And you can see that it's unlikely just because of that high energy. So it takes almost 10 times as much energy to remove that second electron because that's a core electron. So that requires a tremendous increase in energy. So this IE2 was equal to plus 4562 kJs per mole of sodium, plus then reacting to go to sodium 2 plus. And so if we inspect the table, we can see magnesium 738 to 1451 to 7733. So magnesium has two valence electrons, so it has two electrons that it can lose. The second electron took a little more energy than sodium's first, so you can imagine this increase here is coming from magnesium being a little smaller, having a higher effective charge, harder to remove an electron, and then about double the amount of energy to take the second electron off magnesium. And then if we wanted to go to magnesium 3 plus, huge jump. And then we were getting into this kind of discussion next time of like why it is that aluminum is lower has a little bit to do with the fact that sodium and magnesium were losing s electrons, and then aluminum would be losing a p electron. So if we're just thinking of aluminum for a minute, its configuration diagram would be like a 1s2, 2s2, the 2p set of orbitals, and then the 3s. And then the 3p. And if you think about it, we're ionizing these electrons up to infinity. If you remember the kind of Bohr model approach is that we're really just trying to go through the process of taking or understanding these electron configurations for these atoms, and that this electron here is just being removed and excited up to the n equals infinity state. And it just turns out that being in a p orbital puts it higher up in energy to start with. So aluminum has an electron in a higher energy orbital, so that's why the I1 of aluminum kind of drops a little bit from magnesium. If we were to look at aluminum and say, well, how much energy would it take to remove one of those s electrons? And there are ways in spectroscopy that you can remove the s electrons first, or get an idea of what the energy would correspond to removing those electrons instead. And then also you could compare removing these electrons using something called X-ray photoelectron spectroscopy. Sometimes I talk about this as a technique, but I think you can maybe just imagine there's an experimental technique that measures the ionization energy it takes for the one electron versus the other, versus even the core electrons. And what you would find is that the s electrons from aluminum would, of course, take more energy than the magnesium s electrons because aluminum's smaller, higher charge, should take more energy. But it just turns out that taking the p electron, because it's in a higher energy orbital, leads it to having a lower ionization energy. And even then, when we continue on to having an MP4 configuration, spin pairing electrons destabilizes an orbital because of the electron repulsion. So you kind of destabilize the orbital, makes it easier to then remove an electron than what you might have imagined. So when we're looking at our energies to aluminum to silicon increases as we would expect because the p orbital is now smaller, closer to the nucleus, higher charge. Same thing for phosphorus, smaller orbital, higher effective charge, more energy to remove, but then we're spin pairing an electron. So sulfur has that spin paired electron, doesn't take the increase of energy we might have expected, but this is like a spin pairing issue, is why that energy isn't as high as we would expect. And then the aluminum is high because of the s versus the p orbital. So sometimes I just call it a configuration anomaly. We're just taking electrons from different types of orbitals, so they have different ionization energies associated with them. Note that for every, like if we look at argon, for example, as you go from I1 to I2 to I3 to I4 to I5, there's always an increase in energy for each successive electron that's removed from an atom. That's because every time you remove an electron, you reduce electron repulsions. All the other electrons can get a little closer to the nucleus. It takes more energy to remove the next electron. And then whenever we get to the point when we're removing a core electron, then the core electron is always a big jump from the preceding electron. So for silicon, 786, 1557, 30, 3000, 4000, then 16,000. So a big jump when we're removing one of those core electrons. Okay, so this slide here, I think I just meant to delete this slide. So this was in your notes. I just wanted to mention that there's a second slide that's just the same slide as before with a couple different bullet points that are basically the same thing. It requires more energy to remove each successive electron. And then when all the valence electrons have been removed, it takes a great deal more energy to remove that next, what then is a core electron for that original atom. So you can imagine removing all the outer electrons and we get to those inner core electrons, a lot of energy is going to be required to remove one of those. Okay, and so this, we were also talking about this figure last time where we were looking at our left to right trend, seeing the general increase in ionization energy from left to right, just with the configuration anomaly and our NP1 being a little lower. So our NP1 configurations were a little lower than what we expected. And then also the NP4 due to those configuration anomalies, due to the spin pairing for the NP4s and the just taking electron from a p orbital in the NP1 column. And so we're seeing the zigzag, and this repeats itself throughout the periodic table, that we get this periodic inconsistency and the increase in the ionization energy from left to right. And then the top to bottom trend, I think we're getting into this too, is that the top to bottom trend is a general decrease in ionization energy. So you can see for the noble gases that each successive element decreases in ionization energy. You can understand this from the valence electrons moving further away from the nucleus. And if we're thinking our Q1, Q2 divided by D for energy of electrostatic attraction from Coulomb's law, that if you're increasing the distance of separation, the distance of electrons moving further away from the nucleus, then we're going to reduce the energy of electrostatic attraction. But we were kind of reminding ourselves of the fact that effective nuclear charge is actually increasing with this top to bottom trend. So we have two counterposing trends. The increase in effective charge would make you think the ionization energy should have increased from top to bottom, but you can see for most of our elements, we get this decrease. We get a few anomalies where you can see for those, it must be the effective charge winning out. So there's a few cases of elements where you get this increase in ionization energy from top to bottom from the element above them on the periodic table. That's just where the size is winning out. So this is just where the increase in effective charge is winning the sort of the battle, if you will, for attraction on those outer valence electrons. So counterposing trend, further away reduces the attraction, but increase in the charge increases the attraction. You can see that generally, for the most part, the increase in size wins out. So size is increasing by a bigger factor than the effective charge is increasing. If you recall, the effective nuclear charge is just moderately increasing, so it's a small increase from top to bottom, and then the size increase is a pretty substantial increase. And so just trying to understand the ionization energy trends from top to bottom. And so the next topic would be how do we determine the configurations of ions? And these are actually a little bit tricky, because we're going to see that electrons for some elements are removed in a different order than we were thinking about them as we filled them into our elements, like for iron and for calcium. So before we think about the charge of calcium 2+, or iron 2+, or iron 3+, let's think about the charge of in the electron configuration of something like calcium. And so let's think about calcium with the neutral charge first. So calcium is the element 20, so argon 18, and then a 4s2. And then let's contrast this real quick with iron, which is in the same row of the periodic table. So we're also an argon and then 4s2, and then it's a 3d, and it's 6 across. So if we count over to iron, it would be 6 across. And so this is iron with a neutral charge. And so if you're thinking, we kind of put the electrons first. Now, in a way, like, elements aren't constructed by somebody putting electrons into them, right? That's not how elements came to be. So we might write a configuration in a sense that we're putting electrons into one type of orbital, then into another. But we're really just trying to understand those ground state electron configurations so we can get these configurations as correct as possible. And so we come up with 4s2, 3d6 for iron with a neutral charge. So for calcium 2+, you're probably not going to be surprised that we're going to kick those 4s electrons away, because those are the 2 outer valence electrons. So for calcium 0, it had 2 valence electrons, and so probably those 2 outermost electrons would be the ones removed. The cations are actually going to be removed from the largest orbital. If you think of attraction, the weakest attract electrons are going to be the biggest orbital. They're the furthest from the nucleus. So the outermost electrons, easier removed. Those s electrons go away. So calcium 2+ would simply be the configuration of argon. So not too surprising, pretty straightforward, and that's probably exactly what we would have guessed for the configuration of calcium 2+. But then for the configuration of iron 2+, not exactly what we would have expected. We probably would have thought we put the D in last, so why don't we remove those first? Well, think about the size of orbitals. When we were thinking about, our orbitals 1s to 2s to the 2p set of orbitals to a 3s to a 3p set of orbitals, and we had the 4s, where were the 3d orbitals? The 3d orbitals are like here. So that's like one of the d orbitals is right in between the 3p orbitals. So in other words, the 3d orbitals are closer to the nucleus than the 4s electrons. From Coulomb's law, those s electrons are held onto more weakly because they're further away. So it's going to be easier to remove those s electrons first instead of the d electrons. So we're actually going to lose the s electrons. So the configuration of iron 2+ will be an argon 3d6. And that's not like an anomaly, that's just the rule for something like a cation such as iron 2+. And so the book talks about you take the electrons from the highest n value, and then of the highest n value electrons, then the one with the highest L. And so we're looking for the highest n with the highest L. If you think about it, that's just another way of saying the biggest orbital, or the electrons the most weakly held onto by the nucleus. And so then when we're going to iron 3+, we've removed the 4s electrons, those biggest electrons in neutral iron. And so what would be left? Well, the next electrons left are those 3d electrons. And so iron 3+ would remove the 3d electrons, so to go to a 3d5 configuration. So iron 3+ would be argon 3d5. And so we just have to know for cations, removing electrons from the largest orbitals first. So we're going to kick those s electrons off before the d electrons. And that's just the rule for cation configurations. And so it also maybe is helpful when we came back to the idea of valence electrons. So when we're looking at the valence count here, 2 + 6, so 8 valence electrons. And then you can see that 2 or 3. And iron can exist, it's not so common, but there are some examples of like iron with a 5+ charge. You can understand that you can get to some of these higher charged cations just by removing additional valence electrons. Now there's probably good reasons why iron 3+ is stable. If you're thinking about like the half-filled D subshell is usually stable, so we probably get some stability by remaining with the half-filled D subshell. And then other cations may be conformed by removing more of those D electrons. Okay, and so then what about anions? Anions are actually really easy because we just continue to imagine we're filling the subshells that are currently empty or not completely filled. So for oxygen with a neutral charge, configuration is helium. I don't know why we'd write helium, it's so simple. Let's just go 1s2, 2s2, and then 2p4. And then so if we're going to add 2 electrons to O2-, then we're just going to fill that 2p subshell, so not too surprising that our configuration for O2- would just be the 1s2, 2s2, 2p6. So we're just continuing to fill electrons into the orbitals in the order we would have expected into the open valence shells. So nitrogen 3-, Nitrogen neutral is 1s2, 2s2, 2p3, so N3 minus. Of course, it's just 1s2, 2s2, 2p6. So same configuration as O2 minus. So argon with a negative charge. Now, we're going to get to our last topic is going to be electron affinities, the energy associated with absorbing an electron. You can probably imagine O2 minus is relatively favorable to absorb electrons because we have an open shell for electrons. Those electrons are attracted to the nucleus. That's good. The problem argon has is it doesn't have a current shell, so it has to use one of those bigger orbitals. So argon's configuration will look like potassium's configuration. So argon minus will follow from argon 0 of a 1s2, 2s2, 2p6, 3s2, 3p6. For argon 0, make this a minus. We just put a 4s1 in. But that orbital is bigger, not a lot of positive charge. The benefit potassium has, it has an extra proton to hold that electron into place. Argon doesn't have that extra proton. If you think about it, it doesn't really have, if you think of the rule for effective nuclear charge, the Z minus the number of core electrons, there's not much charge that makes it past all those valence electrons to make it out to this electron here. So this really doesn't become a stable ion. This is not going to be an electron that's easily absorbed or likely to be absorbed by something like an argon atom. And you can get a sense of that just by thinking of the configuration of argon minus. Let's point out one other thing to go back to iron 2+ and 3+ for a minute. We can do configuration diagrams. A common question you might see on a test would be something like, consider the configuration of a transition metal cation and then tell us the number of unpaired electrons. Because to get the unpaired electron count right means you have to have the right count like a D6 or a D5. And so we're just picturing that you can still imagine filling electrons into the 5d orbitals. So our D6 would have 4 unpaired electrons. And then the D5, of course, would have all 5 of those electrons being spin unpaired. So a lot of times we'll ask about electron configuration diagrams for some of these transition metal cations so that we can make sure that we have the right configurations. Okay, so think about zinc for a minute. So zinc forms the zinc 2+ cation. It's actually its only common cation that it forms. So why don't you guys take a minute to make sure you can come up with the electrons from which subshell experience the lowest effective charge. You can think about how being closer to the nucleus means the electrons experience a greater charge. Being in bigger orbitals means they experience a lower effective charge. So which electrons and which subshell of zinc experiences the lowest effective charge? And then how many unpaired electrons does zinc 2+ contain? So take a minute or two on this one. Okay, so zinc's an argon 4s2, 3d10. If we were counting valence electrons from chapter 6, we would say that it has just 2 valence electrons. Because once we have this filled d subshell, we're not really counting. If you remember, we count those d electrons when that subshell is unfilled. So we count the outermost shell, highest n value, and then we count any electrons in a lower unfilled subshell. So we would have only said zinc has 2 valence electrons, and it would be strange, I think, if we removed the non-valence electrons first. I think that would seem unreasonable. So we remove those 2 valence electrons first to make zinc 2+ because they're furthest from the nucleus, and that means they experience a lower effective charge. And so experiencing a lower charge further away makes them easier to remove. So 4s easier to remove, and then we're left with the 3d10 configuration for zinc 2+, which of course would have all its electrons spin paired. I mean, maybe we could imagine putting the first 5 in spin paired, and we have to pair up the next 5. And then of course all the argon configuration electrons are spin paired together, so no net unpaired electrons. So a couple other examples of relatively common cations like bismuth 3+. So bismuth is, what is bismuth? It is next to lead, so it's element number 83. And so if we're looking at bismuth, we have a little bit of a trickier configuration. We'd have a xenon starting configuration, and then we'd be thinking, okay, once we get to the cesium row, that's now a 6s2. And we just follow along the elements. We've got to get across all the F blocks. So we got to go across the 4F14. We then got to go across the 3D, 4D, 5D subshell. So we're going across the 5D. And again, I think you can come up with the 5D just from counting the first transition metal row is the 3D, then the yttrium, zirconium row is the 4D, and then the next one down would be the 5D. Kind of cross. And then we come to the P block, where we're putting 3 electrons back in the 6p. And again, if you're forgetting why is it 6p3, you're probably thinking boron's a 2p, aluminum's a 3p, gallium's a 4p, indium's a 5p, tellurium 6p. And so if we're then thinking valence count, sometimes we get really confused on a valence count of something like bismuth, but go up to nitrogen. How many valence electrons does nitrogen have? 5, right? So the whole row of nitrogen should have 5, and then the 5 are these 5 electrons here. So once these subshells here are completely filled, they're not counting towards the valence. It's like, if they're open, we can probably remove some of those electrons to make cations, but if they're completely filled, that like locks that subshell into place. And so our easiest electrons to remove are going to be the ones that are furthest from the nucleus. That's highest N with the highest L. So these 6p3 electrons are going to be the easiest electrons to remove. So we want to remove the highest N, and if we have multiple subshells that share that N value, we want to take the ones from the highest L. This is just another way of saying largest subshell, or lowest effective nuclear charge. So those ones with the lowest Z effective. And so bismuth 3+ would have the configuration of 6s2, 4f14, 5d10. We have this configuration here. Now, lead 2+ is kind of right next to it. So lead 0's configuration was a xenon, 6s2, 4f14, 5d10, and then 6p2. So lead 2+ just doesn't have the 6p2 electrons. So we kick those electrons off first from lead 0 to make lead 2+. So for cations, I think it's easiest to go to the neutral atom first. So think lead 0 first, and then kick the electrons off to make the cation. And then what about lead 4+? Where are the next 2 electrons, where are they removed from in the atom? Not the 5d subshell, that's completely filled, not even counting towards the valence. Not the 4f14, also not counting towards the valence, but the next biggest orbital, the 6s2. So for lead 4+, we'd have a xenon configuration, 4f14, 5d10. Okay, so that's going to be our common configuration, or the configuration we'd expect for lead 4+. Okay, let's see one more slide, and let's look at a couple review problems from chapter 7. So this is a table of electron affinities. So electron affinity is the energy associated with absorbing an electron. So these are the reactions of like H as a gas absorbing an electron to make H minus. Electron affinity for that, so the energy of this reaction is minus 73 kJs per mole. If you consider the reaction like fluorine, so fluorine gas plus an electron goes to F minus. So this is the energy associated with an atom as a gas, absorbing an electron, staying a gas. And so then fluorine's electron affinity is minus 328. And if we're inspecting all of the elements in the table that are shown, the halogens are the ones that are most negative, which probably makes the most sense because from left to right, these are the elements that have both room for one more electron, or at least one more electron, and then also are relatively small and also have relatively high effective nuclear charges. In fact, it's kind of interesting, I don't know, this is like another one of those cases of if you go to chlorine, chlorine is a little bit bigger, so we're putting that next electron in a bigger subshell, but chlorine has a higher effective charge. The higher effective charge here wins out. Chlorine has a more negative electron affinity than fluorine. I don't think that's worth memorizing, but I think it's worth just appreciating that we're just coming back to Coulomb's law, and we have another situation where when we go from F to Cl, that from F to Cl, the distance is going up, but the effective charge also goes up. So which one wins out? And it turns out that for this case, the charge going up won out because it's more it's more beneficial for chlorine, it's more negative for chlorine to absorb an electron than fluorine. And so I just think that's kind of interesting how we have for ionization energy the same problem, but the size trend won out. And here for F to Cl, the charge, the increase in effective charge trend wins out. But then for bromine to iodine, we end up following the size trend. So the second row, well, I guess it's the third row, the second P block. So the 3P subshell is the one that has the most negative energies for most of the case, at least for a few examples. So if you notice for 4 of the 6 elements that the 3P block has the more negative electron affinity. Again, probably not something worth memorizing or anything, but just worth seeing the kind of give and take of size versus increase in charge kind of playing out. Now, the group that has the resetting of the electron affinity trend comes with the noble gases. So the noble gases are the ones that are the most unfavorable. So these are really unfavorable. And they are the most unfavorable of any group on the periodic table. And that's because, of course, they have nowhere to put an extra valence electron other than a higher energy subshell. We have a give and a take here. If I shut that door, it gets hot in the room. If you notice, it got cooler in here. So there's that thermostat there. I don't know why this building's this way. A lot of rooms that are hot, if you just open a door near the thermostat, the room gets cool. But it gets loud. So another real life give and take. So the noble gases, nowhere to put an electron other than a higher energy subshell, so it's really unfavorable. So we reset our electron affinity, most favorable for the halogens, least favorable for the noble gases. And then we kind of go between being negative and then unfavorable and then increasing in favorability. So let's think about the trend, how, like if you're an atom like lithium. So lithium has room for 1 electron in an S subshell, so that's relatively favorable. Beryllium has to put its next electron in a P subshell, which is bigger, further from the nucleus, not as favorable. And so this is just because we're putting the electron into a P subshell. So the next electron has to go into that higher energy subshell, so not as favorable. So we have some unfavorable electron affinities for the alkaline elements. And then the other group that we'd expect to be unfavorable, or more unfavorable maybe than others in the row, kind of like our reverse ionization energy anomaly, would be the P3s, because if they're going to add an extra electron, it has to spin pair. So it has an energy penalty for spin pairing that electron, and so we see that those aren't as favorable as the preceding elements. And so we're generally becoming more negative towards the halogens, but with the anomalies now in the NS2. So we see the NS2 anomaly, and then the NP3. And it's the reverse of the ionization anomaly. It's just we're putting electrons in either to a higher energy subshell or spin pairing. Okay, so the halogen's most favorable, noble gas is least favorable, and then we see some anomalies. But generally, you can see that it's for most of the elements, it's favorable, meaning net negative for the atom to absorb an electron. And that's really just coming from negative electron, positive effective charge, we get net attraction. So once the electron's absorbed into the atom, it takes energy to remove the electron. Think about F minus for a minute. If you had F minus and you wanted to remove an electron off of F minus, do you see how it would take energy? Precisely, it would take plus 328 kJs per mole. So for the elements that are favorable, if they absorb an electron in, then you have to pay that energy to remove that electron back off the atom. Just kind of showing that we have electron nuclear attraction in most of these anions that are forming. So let's try to wrap chapter 7 up with a couple review problems. This is, if you want to follow along, I threw this particular quiz. It's one of the daily quizzes, so it's in that part of Carmen. But I also put this particular quiz into the lecture slides page underneath the chapter 7 notes. And so what statement is true about the periodic table? So Mendeleev was the one assembling the elements in the periodic table. Were most of the elements discovered? So the first thing, Mendeleev assembled the periodic table after, only after most of the elements had been discovered. And he was actually doing this, of course, before a lot of the elements were discovered. So that's not something that was true. So the periodic table was being put together well before several elements were known. And then were we putting elements into horizontal rows or vertical columns of similar properties? And of course, it was the vertical columns. And this is so obvious that it's the vertical columns that are sharing properties. The horizontal rows almost share no properties, other than maybe hydrogen and helium, both being gases. But hydrogen and helium, of course, don't even share the property of diatomic H2, monoatomic helium. So obviously not a lot of property being shared within a row. And then we're putting the periodic table together well before the discovery of protons, neutrons, and electrons as well. And so that's also an interesting observation, is that this is a good 30 years or so before we're really figuring out what even an atom is comprised of. All right, so what do we think about effective charge? And so sometimes I see students get their periodic table for midterm 3 and they go right to it and do the trends so that we can make sure that we know and remember our effective nuclear charge from left to right. Let's actually do this real quick as a quick summary. So we have the main properties here of effective charge, the size of atoms, we have the ionization energy and the electron affinity. And we can think of some of our left to right trends and our top to bottom trends. And so the effective charge, that's the main trend that increases from left to right. That's where we're getting our periodic behavior, and when we reset this every time in the periodic table with each new row. And then from top to bottom, we get that slight increase. So an increase, but just a little bit of an increase. And so a much bigger increase from left to right than from top to bottom. And so, of course, that effective charge is playing a role in the decrease of size from left to right. This is that quick summary. So we get a decrease in size due to the increase in effective charge. And then if you recall, the increase in effective charge is really just the core electrons doing the screening. So that's really the reason why the effective charge is increasing, is just the core are the only electrons that screen the valence electrons, so we decrease in size from left to right, but increase from top to bottom just because more electrons, bigger size, more repulsions, et cetera. So probably pretty obvious that we get the increase in size from having a 1s1, 1s2, 2s1, 3s1. So as we're going up in orbital size for our electrons, increasing the size of the atoms. Ionization energy, we're getting the general increase due to the two trends here, the increase and decrease of effective charge and size. But our ionization energy is increasing, but with that periodic inconsistency in the MP1 and MP4. And then top to bottom, generally getting a decrease. And again, generally because the increase in size wins out. And so this is mostly due to this trend here, and despite the trend of increasing charge. And then the electron affinity is a weird trend. I mean, because the way I like to think of it is it becomes more negative from left to right until you get to the halogens. So how do you say more negative? One way is like decrease. But I usually like to just make sure we're thinking of this as more negative, more favorable. Because sometimes if you memorize or think decrease in electron affinity, for some reason, sometimes we misconceive that to mean less favorable because it's dropping. Dropping is more negative here because they're mostly negative. So those become more negative, more favorable. And then the top to bottom trend, they're, we saw the varying trend of negative, more negative, less negative. So the third row was the sort of sweet spot for electron affinities. Again, the thing I would probably take away from the top to bottom trend is it's complicated. So a hard trend to put to the second row is usually pretty negative. The third row more. The next two rows not as favorable. Okay, so when we're thinking of Na versus Cl in terms of the valence electrons experiencing the greatest nuclear charge, the valence electrons and the charge they experience, that's effective nuclear charge. So this question is asking which atoms have the highest effective charge. So sodium versus chlorine, same row as each other. Chlorine's all the way on the other side, going to have a much higher effective charge. Oxygen versus sulfur. Get a little bit of an increase for sulfur due to the top to bottom trend, so sulfur should be a little higher. So what about the screening of nuclear charge by core electrons? Is the screening identical to the screening by the valence electrons? Is it responsible for the increase in size from top to bottom? Is there less screening by the valence electrons? Or the core electrons screening more than the valence electrons? So this is just getting at, like thinking of maybe something like sodium, 1s2, 2s2, 2p set of orbitals. Are those electrons screening more or less than the 3s? So obviously the core electrons are the ones doing most of the screening. So the screening by the core electrons is greater than the screening by the valence electrons. So in other words, adding 1 or 2 valence electrons doesn't impact that s electron's nuclear charge that it's experiencing. And that makes total sense, right? That adding more electrons on the outside of the atom isn't having a negative impact on the charge that those inner electrons are experiencing. So those inner electrons always get to experience mostly the full charge of the nucleus, and it's the outer electrons that are being limited due to the screening of the electrons in between them, those core electrons. And then the valence electrons don't really screen each other. So the valence electrons at least aren't to a high level screening each other. This then explains the effective charge increasing from left to right. If the valence electrons screened each other as much as the core electrons did, then effective charge would probably be constant from left to right, and then we'd have no reason to explain why our elements are varying in property from left to right. So we have a hard time understanding properties from left to right. And one thing that maybe I haven't really stressed yet is just the implication of the left side wanting to lose electrons more favorably than the right side wanting to absorb electrons more favorably leads to our ionic compounds. So it leads to the type of compounds that are going to form where our left side goes plus more predominantly, the right side goes negative, and we pair up and form ionic compounds. Let's talk about answer B real quick. So it says the screening by the core electrons, that doesn't have anything to really do with the increase in size from top to bottom. So the increase in size from top to bottom is just all about the total number of electrons and electron repulsion, or just using larger orbitals as we go from top to bottom. Let me throw this one to you guys to look at the molecule of ethanol and try to identify the longest bond in the molecule and the shortest bond. And think about which atoms are bigger and which atoms are smaller. Maybe I won't throw it to you guys. Which atom's the smallest in the molecule? Pretty obviously H, right? So hydrogen, helium, those are a lot smaller than all the second row elements. So hydrogen's the smallest atom in this molecule. And then is carbon smaller or is oxygen smaller? Thinking of your left to right trends. So thinking about bonding atomic radii trends, our radius are becoming smaller from left to right. So oxygen's smaller than carbon. And this is just thinking our bonding atomic radii trend. So that was our main size trend, if you recall, was that our size of atoms in molecules, we were tracking them. We even were putting a size. You can actually go to that bonding atomic radius chart further back in the notes and look up the size of O, the size of C, add them together. That would be roughly the CO bond length. Take the size of C, add it to itself, that would be roughly the carbon-carbon bond length distance. I mentioned that chart works well when all the atoms are single bonded. If you start making a different type of bond, like with carbon double bonded to oxygen, then the chart doesn't really work so well at predicting a bond length. But what we can predict, everything's a single bond here, that the CC bond will be longer just because it has the two biggest atoms bonded together. So our longest bond should be the two biggest atoms bonded together. And then our shortest bond, if we were asked, it wasn't asked, so this one here should be the shortest, the smallest atom bonded with the other smallest atom. And if you were even asked a different question, would you expect the OH bond or like an H2 bond to be shorter? Having two smaller atoms bonded together, of course, is going to result in a shorter bond distance than H with a bigger atom of O. And so this one will be even shorter. So you can get a sense of bond lengths by kind of picturing a molecule, thinking about which atoms are bigger or smaller. If you pair bigger atoms together, they're going to make for a longer bond. What about size trend? So one of the things sometimes we're comparing like K plus, Cl minus, Br minus is sometimes we get a little bit confused and we start comparing the sizes if they didn't have any charges. And the fact that they have their charges is really important because potassium with a neutral charge has that extra 4s1 shell that's pretty big. If we lose that shell, potassium plus is a lot smaller. So we have to think about what these ions have in common with each other. For K plus and Cl minus, they share having 18 electrons. And so K plus and Br minus, we call that isoelectronic, just to mean they have the same electronic configuration. So they're both the configuration of argon. And the one with more protons has to be more smaller, has to take the smaller size. If we have the same number of electrons, having more positive particles will pull those electrons in more closely, make that ion smaller. So K plus here is the smallest. And then what do chloride and bromide have in common? What they have in common is that they're in the same row as each other. And so bromide being in the same row has to be bigger than chloride. And so K plus is going to be smaller than chloride. This is because of the isoelectronic series, or because they're isoelectronic and we have 19 plus versus 17 plus. So you have more protons to pull the same count of electrons in for K plus, it goes smaller. And then bromide from top to bottom, bromide's bigger. It's bigger just from top to bottom, we have the increase in size. And so that would be our trend here, K plus to chloride to bromide. So sometimes we have a question like 25 on a test, and just to make sure that we understand that the fourth ionization of titanium isn't titanium losing 4 electrons, it's the fourth electron lost by titanium. So the I1 would be titanium to titanium plus an electron. The I2 is titanium plus going to titanium 2 plus another electron. Titanium 2 plus going to 3 plus is the third. So that's I1, this is I2, this is I3. So I4 is just titanium 3 plus going to titanium 4 plus. And this is just to make sure that when we see an I1, an I2, and I3, that it's just the energy to remove that particular electron. The I2 isn't the energy to remove the first 2 electrons, it's just the energy to remove specifically the second electron. Give and take. Okay, so which member in each pair below has the greatest first ionization energy? And so for this question, we're going to be thinking of applying our general rule that we have that general increase left to right, and then we have the general decrease from top to bottom. So sodium to cesium. Now, if I write a test, like if I picked, silver and gold, pretty tricky, because those are actually the two that lead to the increase. And so that wouldn't be a really fair question. If we write a question, we want you to apply the general trend. And so, especially when the elements are far away from each other, sodium and cesium, we can get that cesium certainly has to have a lot lower of an ionization energy because it's bigger. Sodium having the higher ionization energy because it's smaller. So being in the same row as each other, being higher up, higher ionization energy. And then aluminum and phosphorus. So aluminum and phosphorus are NP1 and NP3 configurations. And so that's not dealing with any of the particular anomalies. So this is just the general increase from left to right. Phosphorus should be higher because it's smaller, has a higher effective charge. I don't think we tend to test the anomaly too much, at least I haven't seen it in a while, where we would give you, so we tend not to say phosphorus for sulfur, which one has the higher ionization energy. And even then, sometimes it's lower, sometimes it's just not as high as you would have expected. So it's really tricky if we give you like adjacent atoms. So usually when we give you comparing ionization energy trends, we want you to be able to apply the general rule, not worry a whole lot about the anomaly, maybe be aware that there are those drops in the NP1, NP4, but usually when we ask you which one's higher versus lower, it's just applying the general trend. So sodium and phosphorus here would have the highest first ionization energies. Occasionally we'll ask a question that is, depending on the elements, is sometimes tricky versus easier to answer. Like imagine we ask like sodium versus magnesium. And we say which one has the higher second IE? And like this question here is a little tricky because magnesium second is a core, so that's probably gonna make sodium have the higher second ionization energy. So sometimes we can get tricky and ask like which one has a higher, third ionization energy, and you're evaluating if one of them has the third electron being like a core electron, which would make it a lot higher than you would imagine an element near it losing a third electron that's still a valence electron. Now, if you get too cute with this, if we say, what about argon's second? Wouldn't surprise me if argon second just happens to be like higher than sodium second. So like if you get an element that's really big, it could be that its second is quite high. So sometimes you have to make sure the elements are close together. So this question here is just getting at core electron removal. So this question here is really just trying to get us to think if we remember or understand that the core electron removal is going to have a lot higher ionization energy. And if we remember back, we might remember sodium was like 500 to 4,500, magnesium was like 700 to 1,400. So a pretty big jump when we're removing core electrons. Configuration of iron 3+, we did that one earlier, but again, we're just removing the electrons from the s orbital first. And this one, if we recall, was the argon 3d5, because we removed the s electrons first. And so that just had all 5 electrons that were unpaired. There's a couple other daily quizzes that will have some other problems on electron configurations of cations. I would make sure over the next couple of days to make sure to revisit a couple examples just to make sure that coming up with cation configurations sets in. Sulfide, S2- just continues from the, oh, it's funny, these are actually all wrong because they technically should be neon. So these should say neon, not argon. But neon 3s2, 3p4, that's sulfur with the 0 charge, adding 2 more gets you to configuration B. So anion configuration is a little bit more straightforward because we're just applying electrons in the same order we were putting them into the elements in the first place. And then the most positive electron affinities are noble gases. And so one of the things to keep in mind is positive electron affinities is bad for electron affinities because they're usually negative, and negative is favorable in terms of energy. And so unfavorable most for the noble gases. So just a short quiz to try to wrap up a relatively short chapter before we maybe get a quick little preview of chapter 8. So chapter 6 and 9, I think are, we've mentioned this a few times, a unit of going from electron properties to nuclear properties, now into bond properties in chapter 8, and then into molecular shapes into chapter 9. So this chapter here, we're going to get into concepts like Lewis symbols, talk a little bit about the octet rule, talk about ionic bonding and lattice energies to describe strengths of ionic bonds. And then we want to get into covalent bonding. This is getting into molecular compounds and getting their Lewis structures. And so then we start talking about things like bond polarity, electronegativities. This was only shaded in red because the first lecture will contain the red section. So we'll eventually cover all of chapter 8. I don't think we skip anything from chapter 8 in our coverage. So we will cover the complete chapter where we get into drawing Lewis structures and understanding them for a variety of different type of molecules. And so there's three actually main types of bonding, and two of them we talk about a lot, and the third one we rarely talk about. And so the three common types of bonding are ionic bonds, first covalent bonds, and then a third important type is metallic bonds. And so let's compare and contrast these bonding types. And so ionic, I think, to me, makes the most sense because this is like where we have the permanent donation and accepting of electrons. So this is where sodium with that extra electron, with that one valence electron, and chlorine needing one valence electron, where sodium loses that electron, gives it the chloride. We end up forming sodium plus as a result. And then you get the electrostatic force of attraction that then results from the plus minus. And so if we think of bonding as being either the permanent donation of electrons and forming ions that then have some attraction towards each other, that's ionic bonding. The case of the atoms that then have such high ionization energies, like hydrogen's ionization energy, if we go back to chapter 7, hydrogen's IE is like 1,300 kJs per mole, sodium's like 500. You can see that hydrogen's not going to give up its electron as easily as lithium or sodium or the other alkali metals. So hydrogen wants to keep its electron, but it still needs another electron to try to fill its octet, if you will, or try to come up with some more stable count of electrons. So we have the sharing of electrons. So our atoms that don't have as low ionization energies or as favorable electron affinities share electrons. And so then we share electrons with each other to make our molecular bonds. And so covalent compounds are then where we're sharing electrons between the nuclei instead of formally donating and accepting electrons into cations and anions. And what about metallic bonding? So metallic bonding is the type of bonding that goes on, of course, in metals. So we're thinking maybe like iron solid. And sometimes when we see Fe solid, we don't think there's a bond there, but there really is a tremendous number of bonds in something like a chunk of iron. And so those bonds are metallic bonds. And so then how do we describe the difference between metallic bonding from ionic, from covalent? Well, if you imagine we have relatively high charges on all these atoms, so we have a lot of valence electrons, and we have high charges of these nuclei that's making out to those electrons. And so you actually have a case where all the electrons in one iron are being like shared across all the others. So you just have all the electrons almost like a fluid. They're being shared across the iron atom. And so this is kind of a completely different type of bonding model. So instead of the electrons being either here and here, we get charges, or they're between the nuclei, we have covalent bonds. What if all the electrons are just everywhere and they're almost flowing as if it's a liquid? And so the properties of an electron in something like a strip of copper can almost be thought of like a fluid. You remove an electron, all the others flow to replace it. And so you get kind of what's called like a sea of electrons as being a model for the bonding in metals. So there is bonding in metals. We talk about it very briefly in chapter 12 when we get there. But I just want us to think that when we see a metal that there is some type of bonding taking place, and that bonding type is really kind of now a third different formal way of thinking of what electrons are doing in molecules. And so we'll get into these topics next week, so this is probably a good stopping point. So we'll pick up with the octet rule, some Lewis symbols, and getting into some ionic bonding concepts on Monday. Have a great weekend. Go Buckeyes. It'll be a great game tomorrow. Who's going to the game tomorrow?